Hi everyone, and welcome to this lecture. Today we are going to see how we are going to tackle inverse Laplace transformations. So you already saw that if you have a function and let's say your function is f of t, and if you take the Laplace transformation of f of t, where this calligraphical is the operation that transforms this function into its Laplace conjugate, so to say, this looks something like this: 0 to infinity f of t e to the power minus st and dt, and it's sometimes denoted with capital F of s, right? So we ask, is there any kind of transformation that, given this f of s is already available to us, can we extract out f of t? That's what the inverse Laplace transformation is. So if I write L inverse capital F of s, this should give me f of t. This is our inverse Laplace transformation, and this can be achieved by the following integral. That means, let me write them down, the conditions. That is, let's say we have a function f of s which is analytic throughout the finite s plane. Obviously this s is a complex variable in general, so we are saying that f of s is analytic throughout the finite s plane except for a finite number of isolated singularities. Of isolated singularities. Then the inverse Laplace transformation can be achieved through the following integral: f of t is equals to 1 upon 2 pi I, and there will be an it doesn't look like integration symbol. So this can be done via this integral: gamma minus I infinity, gamma plus I infinity, e to the power st capital F of s, and the condition that t is greater than 0. This is the integral that is known as the Bromwich integral, and please don't get confused by saying this I infinity is over here. So this integral has a name, it's called the Bromwich integral, and I'm going to show you in a few seconds that how this integral looks in the s plane, that means the geometrical picture. So Bromwich, I hope I got the spelling correct, integral. So if you solve this Bromwich integral for a given f of s, then you will find f of t, and this is the key for the inverse Laplace transformation. So now let's try to see the geometrical picture. So let's say this is my s plane. This is the s plane, and I'm choosing some contour like this. This is the gamma. Okay, and let's say this point has a coordinate of gamma plus IR, and this coordinate, let's say it has gamma minus IR, and we chose this gamma in such a manner that all the singular points of f of s lies on the left side of this straight line. So if my singular points are denoted with this cross, they will look something like this. There might be many singular points, but they're finite. That's what we are assuming, and we have to take gamma in such a manner that all the singular points are on the left hand side of this line. So let's give this line a name. That means we start from this gamma minus r point and we go up to gamma plus r point, like this, and let's call this line as LR. So all the singular points or all the singularities will lie on left of gamma, like this. Even if it's on the real axis or the imaginary axis, it doesn't matter. And this gamma is kind of irrelevant. You will see in a few seconds why. So since we are considering a contour integral like this, in fact it will be a contour integral, it's denoted as the contour integral. I haven't given this O sign over here. However, if you want, you can always go back and give it a contour sign, but traditionally it's not given there, so I'll just use the tradition that has been followed for like years and stuff. So now, since there are finite number of isolated singularities, what we can do is that we can close the contour. That means we can start from here, go up to this point, and then we can close it like this. And this is a semicircle, and let's call this semicircular contour as CR. And when we take r goes to infinity, that's when we get this Bromwich integral. So that's why you will have this I infinity, and I mean plus I infinity, and the minus I infinity over here. That's the idea behind it. Okay, so the main reason of choosing this gamma or writing this gamma is to let you know that you have to consider all the singular points that comes with the function f of s. Alright, and this is the Bromwich contour. This is also known as the Bromwich contour, and if you just do it for any function f of s, you will get the inverse Laplace transformation. Okay, so now we can switch back. Since this is a contour integral, we can switch back to our residue theorem, right? So what we can do is that we can write the integral on LR plus CR. That means this integral over here. So let's call this Bromwich integral as equation 1. So equation 1 gives us the following. That is, it can be divided into two sectors. That is from minus gamma r IR to gamma plus IR. That is on LR and then on the semicircular arc CR. Right. So first of all, let's write the LR thing, and this will have the format of e to the power st f of s ds, right? And oh my god, I forgot to write a ds over here. Yeah, this should be like this. I forgot to mention the ds, and why this 2 pi I is over here, it will be apparent a bit later, so have patience. Right now we are just considering the contour over here, and you can obviously go for this 2 pi I as well, right? And then on the semicircular arc we can write this e to the power st thing f of s ds, right? But this is what? This is a contour integral of e to the power st f of s ds over this whole contour, right? And by residue theorem, I can write the next line as 2 pi I as a sum over the residues times 2 pi I. So the second line is coming from the Cauchy's residue theorem. Keep that in mind. This is the summation over the residues. And if you want to be more formal, you can just write it as n equals to 1 to capital N. That means there is a finite number of singular points, and all the singular points are denoted with s is equals to s of n, like this. Okay, so then you have to write this whole integrand over here, st f of s. Now there are two parts of it. One is this LR guy, another one is this CR guy, right? And usually when r goes to infinity, we have seen that the contribution on the semicircle goes to 0, even though that's not the case always. But it can be proven in general that for for inverse Laplace transformation, that means for any Bromwich contour, for any function f of s that has a finite number of singularities, for any Bromwich contour, the contribution coming from the semicircle will go to 0. So what we will do is that we will say this guy will go to 0. This will be the case, and it can be proven using some parameterization and something called a Jordan's inequality that is involved with the Jordan's lemma as well. Okay, and since this guy goes to 0 and there's a 2 pi I over here, they will cancel each other out, right? And on the left hand side we will have our f of t. So we actually have f of t is equals to the sum of the residues of e to the power st f of s, and that's it. That's all we need to do to find the inverse Laplace transformation, or so to say, to solve the Bromwich integral. Alright, so this is the key formula that will be useful. That means you have some f of s, some function is already given to you that has a finite amount of finite number of isolated singularities. You just pick up some e to the power st and then you calculate all the sum of the residues. That means the sum of the residues for all the isolated singular points. So that's the theory, and in the next video we're going to see some examples of it. Thank you.